Welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier for it to understand. Today we're going to be looking at the velocity in polar coordinates and how to derive them, and where they come from, and we're also going to look at the acceleration. So let's first start defining some things. If I just have a two-plane drawn there, I'm going to put point A over here on this first drawing, and point A over here. This is point A, point A. So let's just repeat that on these one here. Okay. If I want to know the position of point A, what I can do is I can use a vector, right? And I'm going to have a vector that's going to leave the origin and go all the way to A. It's going to look something like this. And this vector we're going to call R. And why R? Just to be consistent with what a lot of books use and what you can see around if you go about reading this afterwards. Okay, on the right case, if I want to define that vector that defines the position, same thing, right? It's going to leave the origin and it's going to go to, to A. Okay, so that's going to be our vector R in that situation there. What about in the bottom graphs? Exactly the same thing, right? On the polar system, exactly the same thing. We're going to have R. And we're going to have R like so. Okay. What is the difference? Well, in the Cartesian system, what we have is we have two unit vectors, right? Unitary vectors, so vectors of magnitude 1. And these vectors we're going to call I hat and j hat. So these vectors are vectors that have a magnitude of 1, right? So it's always unit of 1, unitary vectors, and we use them to scale the vectors that we're looking for. So in this case here, you can see that I'm going to have 2 units on the I direction, or the x direction, which is going to end up over here, right at the bottom here, and I have 2 units going upwards on the j direction. Okay, so I can write vector r as, let me just get rid of that. I can write this vector r as 2 times I plus 2 times j. Right, because I'm going 2 on the I direction and 2 on the j direction, and if I do that, I'm going to end up here. So go 2 to this side and go upwards twice. Okay, so another way to think of this is that I'm going to go twice on the horizontal direction, and then I'm going to go twice upwards, and I end up there. What about on this other case here? What about on this right case here? Well, in this case, I'm going to have my I still in the same place. Okay, stays there forever. My j still stays in the same place. But this time, I need to go backwards 2 units on the I direction, and then upwards 1 unit on the j direction. So if I wanted to write my vector r, then in this case it will be minus 2I hat plus 1 j hat. Okay, and I can do that for any point in this graph that I want. Right? So if my, I don't know, if my r was down here, for instance, then my point was down there, then my r is going to be like this, and I'm going to have -2 negative I and 2 negative j. Right? Because I have both on the negative side. On the polar one, things change a bit. Because on the polar one, what I'm going to do is I'm going to have a unit vector that's always going to point in the same direction as my position vector. And that's what we call r hat. And perpendicular to that, always perpendicular, I'm going to have what we're going to call theta hat. So we're going to take advantage of the fact that, let me get rid of this, r, oops, I didn't want that much, just this guy here. R hat, so we're going to take advantage of the angle theta here, and this magnitude here, to define the position on the polar system. And what that allows us to do is to have a relationship, a mathematical relationship that's simpler. I just need to multiply the scalar, that is, how much I need on the r direction, and multiply that by the unitary vector r hat. Okay, so as before on the Cartesian, what we had was that for any r that we wanted to define, any r vector, what we need to do is give it a number, a scalar, on the I direction, and also give it a number, a scalar, on the j direction. Right? On the polar system, things are simpler, because we just need to give one scalar, r, and multiply by r hat. Okay, so in this case here, that's going to be what's going to happen, and on this one over here, our theta is going to be bigger. But in terms of unit vectors, the same thing applies. We still have r hat over here and theta hat over here. What's the difference? Note that on the Cartesian one, I and j are always the same. They never change, right? Whereas in the polar one, r hat and theta hat, they change according to the position. So we simplify the general equation, but this guy here is always changing with position. And this guy is actually a function. If you notice, this guy is a function. R hat is a function of theta, right? So how does velocity work? Well, we know velocity is how the position is changing with time. And if we go ahead and derive the velocity for the Cartesian one, what we end up is I'm deriving the position in respect to time. And to do that, I'm going to have to take the derivative of this fellow and multiply by this one, and also take the derivative of the, derivative of this second fellow, and then multiply by the first one. And then I'm going to have to do derivative of the first guy multiplied by the second one, plus the derivative of the, I'm all over the place with my eraser here, my second guy multiplied by the first one, right? So what we're going to have is the derivative of how the scalar x is changing with time, multiplied by my I hat, plus my x multiplied by how my I hat is changing with time, plus derivative of y, how it's changing with time, times j hat, plus how my j hat is changing with time, multiplied by my y. The thing is that we know I hat does not change with time whatsoever. It just stays still, and j hat does not either. So these two go to 0. And we're left with a term that looks like this. The derivative of r in respect to time equals how the scalar x, right, the number x that's multiplying my I hat is changing with time multiplied by I hat, plus how my scalar y is changing with time times j hat. And that's it, right? So this is the velocity for the Cartesian one. It's quite simple, straightforward. So the velocity vector, right? When we go to do this on the polar, however, things get a bit more complicated. Why is that? Well, let's try to do it here. Okay, so I'm going to derive, again, the position vector in respect to time. And to do that, I'm going to have to apply chain rule again. I'm going to do the derivative of this one times the second one, and then the derivative of the second one times the first one. So it's going to be derivative of r respect to time. Go ahead and make this a bit thinner. Times r hat plus derivative of r hat in respect to time times r scalar r. And before, on I hat and j hat, this guy did not change with time, but now it does, right? Because we know that as soon as the position of point A changes from here to here, for instance, the r hat's going to be changing from this one here to this one here. So if that's happening, that means that this guy here is not going to be 0. As a matter of fact, we need to find out what this guy is. So let's first define what r hat is, and with that, we can find what's the derivative of r hat. To do that, what I'm going to do is actually going to go back to this idea here. Okay? So if this definition is true, then by definition, that means that my r hat is simply the vector, r, the position vector, divided by its magnitude, right? The scalar that multiply its magnitude, which makes a lot of sense, right? But we also know that this guy here can be we can write that down in the Cartesian coordinates as this, right? So I'm going to go ahead and substitute that. So this is going to be just x times my I hat plus y times my j hat, and all of this divided by r. So what are we saying here? We're saying that our r hat, the thing we're after, right, this guy here, is the same thing as having my x scalar divided by my r scalar multiplied by my I vector, plus having my y scalar divided by my r scalar times my j hat. And what is that? Well, that's quite simple, right? Because let's draw one more time the two plane here. If I have my position over here, I'm going to have my r vector here. And we know that this distance here is r, right? It's magnitude r by definition, right? So this distance here is what we call r, and it's this guy here, this r here. Okay, what about x? Well, x is this distance here, right, on the bottom. Let's do that with blue so it's easier to see. This distance here on the bottom. And y is this distance here. Okay? And we know there's a relationship between it because of theta. Right? Because if we take the sine of theta, that will be simply y, distance y, divided by r. And the cosine of theta, is the distance x divided by r. So I can sub in where I have x over r, and where I have y over r, I can sub in sine and cosine of theta. Okay, so this guy is going to become, this equals the cosine of theta times I hat plus the sine of theta times j hat. Okay, so we just defined our hats. So let me summarize this whole thing we just drew. Okay, so we're saying that, let's do that in green. We're saying that r hat can be also understood as the cosine of theta times I hat plus the sine of theta times j hat. All right, so now we can try to derive this. Okay, so we can try to derive this, and we're going to, if we need to derive this, we're going to have, let's just make this thinner. If we need to derive r hat in respect to time, what will happen is, once again, we're going to have to derive this fella, then multiply by this fella, and then inverse, right? Derive this fella, multiply by this fella. Okay, just one detail, theta is also a function of time, if you remember, because it's also changing with time. So that means that we have to apply the chain rule here. We have to derive the cosine function and also the theta function. Right? So what's going to happen here? We're going to have the derivative of cosine is negative sine of theta times the derivative of theta in respect to time times I hat plus everything the same, cosine of theta times the derivative of I hat with time plus the derivative of the sine, that's going to be the cosine of theta times the derivative of theta because of the chain rule times j hat plus everything the same, sine of theta times the derivative of how j hat is changing with time. Okay, and if you've been paying attention, you know that from what we talked about here, derivative of I hat and derivative of j hat, they don't change with time, right? They're 0. So that means that where we have those fellas, that is over here, and over here, these guys go to 0. That simplifies our relationship. That says that the d hat, dr hat, dt equals minus sine of theta, derivative of theta with time, I hat, plus the cosine of theta, derivative of theta with time, j hat. Okay, and that's almost good, except it's a bit messy. So let me go ahead and take, because we have the derivative of theta multiplying everything, let me go ahead and take it down and put it out of the parentheses like that. So that's going to multiply negative sine of theta times I hat plus the cosine of theta j hat. Okay, now this is very interesting because actually this guy inside the parentheses, this fella here, is actually equal to theta hat, and I'll show you that. Okay, so let's actually see that that's theta hat. Do you remember where we defined r hat over here, and how we were looking at the combining the I components and the j components to find the r component? So same thing applies now. We want to find theta component, right? So let's go ahead and draw again the two-plane axis. And once again, I'm going to draw my r hat, and I told you that we defined, sorry, not r hat, just r. We defined theta hat to be always perpendicular to r hat. Okay, so let me go ahead and let's see if I can increase this drawing, make it a bit bigger. Okay, not as pretty, but still exactly what I wanted to be. Okay, note the following: this guy, this angle here, is theta, right? So if that's theta, that means that this guy also has to be theta. Okay, these two, there's a 90-degree angle between the two of them. Okay, so if I do another 90-degree angle here, yes, another 90 here, then what do we have? Let's actually we'll draw this one more time. Or here, theta here. Boom. Okay, we know that there's theta here, and this is 90 degrees, so 90 degrees here. So that means that this guy here, this angle here, has to be 90 degrees minus theta, right? However, you do copy paste, do that one more time. However, we also know that these guys here are 90 degrees, right? So whatever was left, oh, come on, let me out. So whatever was this angle here that we're interested in, that has to be 90 minus whatever this angle here is, right? And we know that that angle is 90 minus theta. So that means that this green one here has to be, get this out of the way, has to be 90 minus theta. So 90 minus 90, and negative theta with negative theta, that is positive theta. Okay, so to simplify, this angle here, from the start, I'm losing all my letters today. Okay, so this angle here also has to be theta, right? So if that's the case, what does that mean? Well, if I want to define this vector here, it goes like so. Then in terms of I and j, then I need to multiply by a negative number on the I direction, because it needs to go that way, and a positive number on the j direction. How much, what's the scalar that I need to multiply by? Well, I need to multiply by this much here. And this much here is exactly the sine of theta, right? Sine of this guy, sine of theta over here, sine of theta, equals x divided by r. And the cosine of theta, which is this green part here, is going to give me cosine of theta, will be y divided by r. So if I want to define my theta hat, that will be equal to negative, because I need it to be negative on the I direction, negative sine of theta times I hat plus positive cosine of theta j hat. Okay, one more time. This here, sine of theta, oh, that's a horrible color combination. Sine of theta is the same thing as x over r, which is precisely this distance that we need here for this angle theta, because we know the theta hat is a unit vector. And this guy here, cosine of theta, that is precisely this distance, this green distance here, which is y divided by the magnitude r. Okay, so if you remember, why were we doing this? The reason we were doing this is because I told you that theta hat was actually exactly what we had inside the parentheses, and there you go. Okay, so it's exactly the same. So that means that the derivative, let's if we go in here where we were, the derivative of theta hat equals derivative of theta in respect to time theta hat. And that took forever, didn't it? That's why it's more complicated. Let me write it nicely. Derivative of theta hat in respect to time equals derivative of theta in respect to time times theta hat. Now I can go back to where we were on the start. And what we wanted from the beginning was to derive the vector r in respect to time. And the whole thing we just did was to be able to find this fella here. Okay, so now we can rewrite things once again, because we know that this is equal to the theta t times theta hat. Okay, so let's go ahead and rewrite it. So the derivative of the position vector in respect to time will be how the scalar r is varying with time times r hat, plus how the theta is varying with time times theta hat times r. And that is the definition of the velocity in polar coordinates. But that looks complicated, so what we do is we tend to split this into two components, what we call the radial component and the transverse component. Okay, so we simplify this. So this is the velocity, right? Velocity vector. So we actually write it. The velocity is made up of two components: the r, the radial component, times the hat, r hat, sorry, and the theta, the transverse component, times theta hat. Okay, and just by looking at this, you can see that the r is how the scalar r is varying with time, and the theta is how theta is varying with time times the scalar r. And so this is the radial. This is the radial component, and this is the transverse component. Okay, and then obviously, like before, whenever we have two components, and they are perpendicular to each other, right? So we have velocity here, That's made out of two components. One is the transverse, one is the radial. So that means that the magnitude of this guy here, if we want the magnitude of r, then we need to take the square root of the square of one and the square of the other one. Okay, so that's the magnitude of the velocity. Always have to take into account both components. All right, but now if we want the acceleration, we have to do it one more time, right? It's not as bad now because we already have the definition of things. So if we want the acceleration, what we do is we take this fella here and derive it one more time in respect to time. It won't be as hard now. I'll probably just leave it there. Okay, so what are we doing now? We're taking the derivative of the velocity in respect to time, and that's the same thing as taking the second derivative of the position dr in respect to time. And that will be the second derivative of scalar r in respect to time times r hat plus dr dt, derivative of r hat dt, and we know what the definition for this guy is already, plus the second derivative of theta in respect to time times theta hat and r, plus this is varying with time, and derivative of theta hat in respect to time, plus times r, plus the derivative of theta in respect to time, theta hat, and the derivative of r in respect to time. That's a big one, isn't it? Okay, but we know some things already, right? We know what this guy is. We've defined it already. The only thing we haven't defined yet is this fella here. That's quite simple because we already have that fella. It's right there. Okay, so we can derive this guy here in respect to time too. And we're going to end up with the sine of derivative of the sine is a cosine, so it's going to be cosine of theta. Chain rule, you also need to derive the function inside. Multiply with this, plus, or negative I should say, negative sine of theta and the derivative of I in respect to time. No, that's going to be 0. Plus the cosine is going to be negative sine of theta and chain rule, theta in respect to time, j hat, plus derivative of j hat times the cosine. Okay, now again, we know this guy is 0. We know this guy is 0, which means that this is simplified, somewhat simplified, I guess, to how theta is varying with time minus the cosine of theta I hat minus the how. Sorry, should put this outside, like so. Minus sine of theta j hat. Okay, so negative sine, negative cosine. And from this, you can see that this is actually quite similar to this definition here. Oops, not this one here, the R1, right? Where is it? This guy. Okay, so we can actually substitute as R there. So we're going to have the derivative of theta hat will be minus derivative of theta in respect to time times R hat. Okay, so now we can substitute that in, and it takes forever, but things are coming from now. And we can substitute for where we have this guy, we know this is equal to theta dt theta hat. So this whole thing becomes, let's rewrite it one more time. The second derivative of the position in respect to time equals the second derivative of the scalar r in respect to time times theta hat plus how r is varying with time, the theta dt theta hat plus the second derivative of how theta is varying with time, theta hat r plus how theta is varying with time, and this I'm going to substitute by minus the theta dt, so it's going to be squared there, times my r hat times r plus how my theta is varying with time, my theta and your dt. Okay, so now we're going to have some common links here. Everything that's multiplying my r hat, so this guy's multiplying r hat, these guys are multiplying r hat, I'm going to put in one side, and everything else is multiplying theta hat, so this guy, and this guy, I'm going to put on another component. Okay, so I'm going to rewrite this as derivative of the position, second derivative, so the acceleration will be equal to r hat, that's multiplying the second derivative of the scalar r, plus, or minus I should say, negative, minus the square r times the square of how theta is varying with time, plus theta hat, that's multiplying. What do we have? We have 2 times the same thing showing up, so we have derivative of the r dt and d theta dt over here, and also over here, so 2 times the derivative of r dt theta dt plus the second derivative of theta in respect to time. Okay, and there you have it. That's actually the composition of the acceleration. Okay, and again, because this looks very complicated, what we do is we say, okay, the acceleration has 2 components. We have the radial component and the transverse component. So we could just say AR for radial component. Let's go AR times my r hat plus my a theta multiplying my theta hat. And then this guy, obviously, AR is this guy here. A theta is this guy here. I'm going to leave that color because it just doesn't blend well. Let's see if I have another one here. This one maybe? Nope. I guess it's as good as it gets. And then again, this is going to be my radial. And this is my transverse. Okay, finally, just to finish off, the last thing I want to say is, again, if I want the magnitude, if I'm after the magnitude of the acceleration, if I want the magnitude of the acceleration, then I'm going to have to take the derivative, the square root of the square of the radial component and the square of the transverse components, right? Because we have 2 components that are that together make up the acceleration. Okay, we define, just so you know, the derivative of how theta varies with time. So this guy here, that's what we call the angular velocity, and this guy here, the second derivative, is what we call angular acceleration. Okay, so hopefully that was somewhat easy to understand. I know this is not as straightforward as it could be, but hopefully coming from this first analysis, you were able to understand how we got the velocity for the polar coordinates with the radial and the transverse components, and the acceleration for the polar coordinates with, again, the radial and the transverse components.